So we'll start. Last we discussed the one derivation in the last class. I think some people are having some doubts. Yeah. Who asked the one doubt? I don't know the name. I didn't.
Sir, Rishita Shri.
Yeah. Tell me what is your doubt now?
Sir, in the next page, sir. No, sir, the minus RA2, sir.
Hmm.
Why is it considered a homogeneous? Because there is no gas term, like concentration term in that step. Why is that?
So since here minus is there, you are thinking it is heterogeneous, and here only one term is there, you are thinking it is homogeneous. Am I
No,
right?
not like that, sir. The reaction is based only on that surface of B is solid, sir.
Ah, yeah.
So why is that gas term concentration not included in that reaction step?
Now, the example is coal burning, right? Coal is burning. Now, gas is here, right? The gas is going from the bulk onto the surface. How much of the gas is going onto the surface? That is what this reaction is giving you. This is the flux of the transfer of A. A is the gas, right? A is the gas. B is the solid, right? So, the flux of gas through gas film by diffusion per unit surface of the B, how much it is going on to this surface of B is what is giving you by this equation. Now second one, the rate of reaction based on the unit surface of B. Now the gas is sitting here on the surface. So how much it is getting reacted, or how much because of that gas this solid is getting burnt, right? Coal is getting burnt and forming as ash and unburnt thing. So how much it is burning, that depends on the rate at which it is burning into the concentration of that particular surface. Here CAS in the sense it is a CA. What is A? What is A? A is the gas. Concentration
Yes,
of
sir.
gas on the surface. It is not the solid here. CAS is not the solid. S is not solid. The Ca is the concentration of gas which is present on the solid, right? S is the solid here.
அடா பாவி
Okay, sir.
நல்லா இருப்பீங்க எனக்கு இது கொடுறா இன்விடேஷன்
என்னப்பா
சொல்லுக்கா
இது
நானே உடனே சோகம் இருந்தா நினைச்சேன் நாடா
some comedy bit is going on. What is happening? Is it memes, sir? Okay, no problem.
Thank you, sir.
Hirshita, you understood what I mean to tell?
Yes, sir. Yes, sir. Yes, sir.
This you are taking as a gas only. This is it's not a which
Okay,
the
sir.
concentration of gas which is present on the solid, right?
Okay, sir.
This is the
Right.
concentration of gas in the bulk. CAG is the bulk, that is which is in the gas. CAS is the concentration of the gas on the solid.
Okay, sir.
Yeah, both you are writing the concentration of gas only.
Okay, sir. Thank
Did
you,
I
sir.
answer your question or still it's confusing?
No, sir. I'm clear now. I'm clear.
Okay. Any other?
Yes, sir.
Yeah.
Sir, I was confused as to the if kg and k double prime have the same unit.
Yeah. No, it may
I'm-
not be, because I earlier itself told you this is based on this, because these two will have the same unit, but based on that this will different. That is what we got here. Now you see this is having one unit, this is having one unit. This RA prime is based on W, whereas RA is based on the volume. If I know one particular rate and I know the other one, you can see here minus RA into V is RA prime into W. So if I know what is the unit of W and unit of V, if I know the unit of RA known, then I can find out the unit of RA dash. So the RA and RA dash or RA prime will have different units based on what you are taking. But you can convert from one form to the other form. Yeah, that is what. Now you see, I know this particular thing. If I want to calculate this, RA into V divided by W, I'll get this particular thing. Understand? Yeah.
But sir, if you see that equation, it's being
Yeah.
multiplied with the concentration term in both cases. Not here, sir. The other one, where both equations are there.
Yes, yes.
So kg is being multiplied with the
Yeah, this definitely this kg and k prime will have different unit.
But
Kg
sir,
is
then
the mass transfer coefficient, which will have a unit of meter square per second. This kg is the mass transfer because this is the rate of mass transfer. So rate of mass transfer is nothing but the rate of mass transfer is proportional to the concentration. If I remove that proportionality, then I get mass transfer coefficient. Either it is overall or individual. This is actually individual into concentration difference. So this will have a unit of meter square per second mass transfer coefficient. Whereas this is the rate constant because this is the reaction happening. Therefore, reaction is nothing but concentration term into the kinetic term. This is the kinetic term. So definitely this unit and this unit will be different. Yeah.
no, so my point is that they're both being multiplied with a concentration term in
what?
CAG minus CAS. So when you try to equate them in the end, they won't be dimensionally consistent, sir. We're saying that kg has different unit, k double prime has different unit.
It
And
won't. That's what. Based on that only, you are going to calculate what is the unit of k prime, or what is the unit of kg, because you are assuming that how much is the mass transfer is going on, how much is the gas is being transported, that much is what you call reacted. Based on that only, you are trying to calculate, equate, and then get an expression. Now you are getting CAS in terms of this particular thing. So if you use these two units are same, then only you can multiply it. You can add it. Then this gets cancelled out. So CAS and CAG will be having the same unit because concentration should have the same unit.
okay, so yeah, makes sense. Got it.
You see here there is because when the coal is burning, one thing I like to, you get a lot of doubts. I know. I think you are not still thinking here. I am making a steady state assumption. Under the steady state only, this will be true. But there may not be steady state which is reaching there. Can you imagine what is happening now? You see, you imagine there is a coal. I think I'll just draw here. I'll just draw it here. You imagine there is a coal particle here, and there is a gas particle which is coming here. This is solid. So what I mean to tell is this is the solid surface, and this is not forming any ash. This is not forming any ash, right? So this is CAG. This is CAS. So what is telling you is this particular thing is going, then reacting here. What actually, if there is, you are not assuming ash is formed, but if there is ash formed, then what will happen? Your core will go on decreasing. Correct? Your core will go on decreasing. So the length of this path, initially it will be here. After some particular time, if your reactant, the solid is reacted till here, it increases. Am I right? This part is increased. So you can never make that assumption that this you call as a pseudo steady state assumption. You are assuming that the path which the molecules is passing is same, but actually it may not be same. It may be different because initially it is less, but finally after some time it's still, because it should penetrate through this ash layer also to go to the unreacted core, because the reaction is happening only at the unreacted core, right? This you will better understand when we go for still that catalytic reactions and especially the solid catalyzed reactions. We make that assumption, pseudo steady state assumptions. Okay. So here, what is actually your thinking is, we are trying to write an expression for the overall rate of reaction of a gas which is reacted on the solid to give you a gas. So here you are making some assumptions that first order of with respect to A, no ash is formed. So if you want to have that, if you want to formulate this, here since there are two phases, each phase will have one resistance. That is what he tells. You assume, engineering way of doing it is, when there are two phases and where there is a resistance in this phase and this phase, you are thinking that the step 1 is the resistance in the gas phase, the step 2 is the resistance at the solid surface. If you can make an assumption that how much is going in, that is step 1 is equal to step 2, that is how much of the gas is moved or in the gas film is equal to how much is being reacted, then you can get the unknown concentration. So the overall rate can be formulated by considering number of steps. These are the steps. We are assuming that a gas is transported from the bulk of the gas to the solid in the gas film, then the reaction, and then the desorption. Out of these three steps, what we assume is, if you want to write the overall expression for this, you can take only the first two steps and then write the overall rate. The overall rate in heterogeneous system is called as global rate, right? Global rate. Whereas in homogeneous, it's a overall rate or whatever you call. But here we call it as a global rate because there is a phase changes. So desorption is not required. How much the product is transported back, how much we are always bothered about how much of the B is converted, not how much of the R is being formed. So if you want that, you take only the first two steps and write the equation for the first one. This is the mass transfer and this is the reaction. So write the equations for both. Then you assume that how much of the gas is being going in the first step is equal to that much of the gas is being reacted. It's obvious, right? How much. So that is what we are trying to do here. The rate of mass transfer of A through gas film by diffusion per unit surface of the B. You are writing the rate of mass transfer in terms of, you know how to write that rate of mass transfer, that is mass transfer coefficient into the concentration gradient. The concentration gradient is CAG. CAG is nothing but the bulk. CAG is nothing but the bulk concentration. This is the bulk concentration. This is the at the solid concentration. We definitely know that the bulk concentration is much higher. Then only the gas is being moved. If the concentration is uniform, definitely there won't be any gradient. Therefore, the rate of mass transfer will be 0 because the concentration gradient is 0. If you are applying now here one scent bottle, if I open one scent bottle, immediately you will get the fragrance because here the concentration is more. At your level, the fragrance concentration is less. Therefore, there is a gradient. Therefore, the concentration is moving. That is, the scent is moving. How much it is moving, that is what this equation will give you. How much of the gas is being transported, it depends on its mass transfer coefficient. in gas phase because the gas is being moved. So that much again the rate of a reaction based on the unit surface, how much of the gas, that gas is reacted on the surface, therefore minus Ra2 based on the surface is Ra prime into CAS. These two steps are in series. Generally at a steady state, how much of the gas is being moved or transported, we are assuming it that much of is the reaction. There is no accumulation there because steady state in the sense there is no accumulation. How much is gas moved? There is no escape for the gas. It has to react. It cannot stay like that without reaction there. Even though it is there, you are assuming it is steady state. So there is no accumulation inside. So if there is no accumulation, input is equal to output. This is the reaction. This is the input, how much is going. The flux of A to the surface is equal to the surface reaction because accumulation is zero. Right? So this is the equation. If you equate both, then you get the unknown concentration, that is CAS. CAS, we don't know how much is CAS. So we can calculate CAS in terms of kg, CAG divided by K prime plus kg. If we know the mass transfer coefficient and the rate of a reaction, and we know this bulk concentration, then you can calculate CAS. If you resubstitute this in this equation, we can get the overall rate. So if you substitute that CAS here, then you are getting this particular equation. This equation is very important. This equation is very important. Here one thing is this term. If there is a homogeneous reaction, A gas plus B gas is giving you some R gas, then you will write Ra is K times, if this is K, Ca into Cb, that is concentration of A into concentration of B. This is K because you are assuming it is homogeneous. But since the reaction this is solid, we cannot write this K like this. This is the overall. So there are two resistances here. One is gas film resistance and the other is the solid resistance. So you have to write the overall resistances. K overall is nothing but 1 by 1 of individual plus 1 by individual. So you have to write like this. So you are getting this form. This form can be written in terms of 1 by the like that. That is what we tried to do on the last class. So if you do, if you equate this particular thing, if I can write like this, yeah, you can. I'm writing here. So minus Ra prime 2 is 1 by K prime plus Kg divided by K prime Kg into CAG. CAG at the numerator, right? I'm taking from here down. So if you cross multiply, because this is A plus B by C, we can write as A by C plus B by C. So minus Ra2 prime is equal to 1 by K prime by K prime Kg plus Kg divided by K prime Kg into CAG. CAG I am writing here itself. So this prime cancels. This Kg cancels. So what you are left with, Ra2 prime is nothing but minus, that is the disappearance, CAG, that is 1 by, or CAG divided by 1 by Kg plus 1 by K prime. That's all. That is what I am writing here. So this is nothing but, if it is a homogeneous reaction, I am writing minus Ra is K into Ca. But minus Ra prime, this is for that other reaction, is nothing but 1 by Kg plus 1 by K prime CAG. Sorry. Yeah. We are writing CAG. So this K is nothing but this. The K in homogeneous is equal to the K in like this in the heterogeneous. So this is nothing but the sum of the individual mass transfer coefficients. This is in the gas film, this is in the solid, Therefore, the individual sum of the individual resistance, the reciprocal of it will be equal to 1 by this one, right? So that is what is writing here. This is the overall expression for the overall rate in terms of bulk reactant concentrations. Bulk reactant concentrations. Am I right? So by analogy, with the mass transfer coefficients, the sum in the denominator, what is the sum in the denominator, may be regarded as the resistance offered by the individual heterogeneous process. Now 1 by kg is nothing but the resistance offered in the gas phase. 1 by k prime is nothing but the resistance offered in the solid phase. So 1 by the sum of the resistances is nothing but the overall resistance which is offered in the heterogeneous system. So the denominator is the sum of reciprocal rates of individual steps. This is the first step and this is the second step. So when there are two steps in the denominator, we can do, because there are two steps. Out of the two steps, not always two steps will be playing an important role. Sometimes kg will be playing an important role. Sometimes k prime will play an important role. So case number 1. So based on this, 1 by kg is nothing but the resistance. Am I right? 1 by kg is nothing but the resistance in gas phase. 1 by k prime is nothing but the resistance in the reaction. Now, based on the amount of kg and k prime, you can make 1 by kg either it is less or more. So the overall rate of the heterogeneous process is determined by the slowest step, hence it is called as the rate controlling step. Rate controlling step is nothing but if kg is very high, then what will happen to 1 by kg? Kg is mass transfer coefficient in gas phase is high. So 1 by kg will happen to be the resistance in the gas phase. So 1 by kg will be less, correct? You understood, man? So if kg is more, 1 by kg will be less. If kg is more, then k prime, if it is less, 1 by k prime will be very more. So you are adding a very less quantity with a very more quantity. Therefore, 1 by kg can be eliminated. So you get 1 by k prime. Therefore, k prime CAG you get. That is what is this. If kg is greater than k prime, that is the mass transfer coefficient in the gas film is much higher than the rate at which of the rate of the reaction, then the overall rate reduces too. Since kg is very high, 1 by kg will have a very less value, that is the resistance here is very less. Therefore, this term can be safely neglected. So you are dealing with, you can see here, minus RA prime is equal to 1 by, this is very less number, plus 1 by k prime. This is very less number. This already is more number, because since this is less, this is more, this will be less. So since this is more, this can be less. 1 by less value will have a more value. So more value plus something, it is like a 0.0001 something. So more value plus you are adding a very less quantity is nothing but more quantity. So you only this term you can keep. 1 by k prime is nothing but k prime into CAG. That is what you are putting here. Which simply implies that the reaction, chemical reaction, is the rate controlling steps. When you are having Kg is greater than K prime, your equation is turning into minus Ra prime is K prime into Cag. This implies it is reaction control because you are getting reaction term here. So when you are writing like this, then what does this Kg mean? Kg, very high Kg mean? Kg very high in the sense mass transfer coefficient is very high. When the mass transfer coefficient is very high, the diffusion will be very high. So the diffusion is very high in the sense the diffusion is very rapid, but the reaction is very slow. What does this mean? Yeah. Can anyone give a view of it? How you visualize that? Boys, girls, are you with me?
Yes, sir. So maybe it could be like there is a continuous flow of air over the coal, and only the reaction determines the rate of the reaction.
Good. Any other answer? What does this Kg diffusion is rapid, but the reaction is slow? What does that mean? How you can visualize that? I'll put the other way around now. Let me go to the next step. Now let us assume your K prime is greater than Kg. Then what will happen? If this is greater than Kg, then what will happen? I'll just put here. I'll just again work it out. 1 by Kg plus 1 by K prime. Now I am assuming it is K prime is much greater than Kg. So K prime is much greater than Kg. So 1 by K prime. Yeah. 1 by K prime. This is much higher. 1 by higher will have a less quantity, correct? Will have a less quantity. So 1 by Kg. Kg is lower. 1 by lower will have a high value. So high value plus very less value. So this can be safely neglected. So you are left with 1 by Kg. That is nothing but minus Ra prime is nothing but Kg Cag. You get like that, correct? The second case, this is case 2. Case 1 is this. Case 2 is this. If Kg is higher, you won't get Kg here. You get the other one. Whereas if K prime is higher, you get the other one here. Now, if K prime is higher, then what you call here? The reaction is rapid, whereas the diffusion is slow. Since the diffusion is slow, you call that particular case as diffusion controlling step. Diffusion is the rate controlling step. I'll just run through that. Now you see, if K prime is greater than Kg, this is what you are getting. This is called as the mass transfer is the rate controlling step or diffusion, and the reaction is very rapid. That is rapid surface reaction. In some cases, if both are equally important, that is not only Kg, even K prime is important, your reaction holds good here like this. So this you can call intermediate between a chemically controlled region and the mass transfer controlled region. When there is like that, you get the entire equation like this. But if there is a chemically controlled region, then what is the equation change? Chemically controlled region, you get like this equation, and if it is a mass transfer controlled region, you get like this equation. If there is nothing controlled, both steps are equally important, then you get like this. Yeah, I did the derivation. Now let us visualize what is happening to this. What does this diffusion is rapid and reaction is slow? Yeah. Now you know both the cases. Yeah, I want some answer from you. and not the same person who is giving me the answer. Some other. Yeah. Mr. Chiranjeevi, you are there? Chiranjeevi? Mr. Chiranjeevi, you are there or not? You are there or not? No one. Again, as usual, you want me to call out some numbers? Yeah, 62 people are there. Vignesh, please take the attendance. I think 62, only some 61. So some 5 to 6 people are absent. Okay, good. Yeah, Mohammed, Roshan, Rila. Yeah, what does you understand from this equations?
Yes, sir.
Whatever. Yeah, what does this mean? Diffusion is rapid, reaction is very slow. How you visualize that? Or mass transfer is the rate limiting, whereas surface reaction rapid at this reaction is rapid at the surface. How you visualize? The question you understood what I'm asking? There are two cases.
No, sir. Can you please repeat the question?
Yeah, there are two cases now. Kg is greater than K prime, or K prime is greater than Kg. So if I'm assuming Kg is greater than K prime, I'm telling it is chemical reaction is the rate controlling step, whereas K prime is greater than Kg, I'm telling you that mass transfer is the rate controlling step. How you can visualize that? That is what I'm asking. What is happening there? What is happening? Yeah. Any other boy, girl?
Sir.
Yeah. Go ahead. Mohammed? Yeah. Go ahead.
I guess when the diffusion is rapid, the rate of reaction is slowed because the time of contact will be reduced.
Okay. Good. Any other answer?
Sir,
Any other? Who is this? Yeah. Go ahead.
Shweta.
Yeah. Go ahead.
More amount of gas gets accumulated around the cold surface, but the reaction is very slow in the surface.
Very good. Very good. I'm talking about the resistance. What does that mean, resistance? There. So here, when I'm talking about this Kg is greater than K prime, which implies that chemical reaction is the rate controlling step. Rate controlling step in the sense the resistance will be higher in the chemical reaction. What does that mean? Now I gave the answer itself. What does that mean? What do you mean by resistance there? Yeah, think about something in terms of resistance. If I gave the answer itself, just you refine that answer. Yeah, Rajalakshmi. Are you there, ma? Rajalakshmi? You're not there. Sanjay. Mr. Sanjay. Sanjay. என்னம்மா எல்லாரும் ஆஃப் பண்ணி உட்காந்தீங்களோ? ம்? விக்னேஷ். Yeah, Vignesh, go ahead. What does you mean by that here? What do you mean by this? Chemical reaction is rate controlling. What does that mean? Mass transfer is rate controlling or chemical reaction is rate controlling. What does that mean?
Sir, for Kg greater than K prime, sir.
Yeah.
It's said that the diffusion is rapid and reaction is slow. So
yes.
Some greater form of resistance is slowing the reaction. That's what I'm able to decipher from now.
What does that mean? No, you are just reading whatever it is there on the slide. That is correct. What you told is absolutely correct. How you are going to visualize that? Yeah, it is nothing but the resistance. One resistance is much higher than the other resistance. What does that mean? What does that mean? Yeah, I'm spending a lot of time in this particular step because if you can understand this, the entire CRE will be very easy. Otherwise, it becomes like a Vitlacharya movie only. This becomes that, that becomes this. You know, right? Vitlacharya, one director. Hero becomes a cat, heroine becomes snake, like that. Jagan Mohini or some movies are there where he's a great director. Hero will not be hero. Till sometime he will be hero and then he will become a cat or dog or something like that. Right? So reaction engineering also becomes like that. This equation becomes that, that equation becomes this. If you are not able to understand what do you mean by this rate controlling step, based on that I will change my equations based on that. A big numerous amount of equation, I'll make it as a very small, taking into consideration that I'm assuming this is rate controlling. Yeah. What does that mean? Or how you visualize that? Yeah, any other answer?
Mean that there's no concentration gradient in the gas phase and mass transfer phase.
Anita, yeah. Go ahead, ma. I didn't hear what you told. Yeah.
Because of the rapid diffusion that will be there with the surface reaction, there'll be no concentration gradient.
Very good. Can you refine on what you told? What do you mean by concentration gradient there? Yeah, Anita, what you told is absolutely correct. But I get doubt whether what you told, whether do you mean it? Do you understand what you told? What you told is absolutely correct.
Because when the reaction is very low, sir, the 1 by kg will become very negligible. I'm not sure how to explain it, sir.
Yeah. I can understand. Yeah, go ahead. Whatever you. Yeah, I'll just put that slide. Yeah, tell me. Now tell me.
Because when kg is very greater than kg prime,
yeah,
the 1 by kg becomes very negligible.
Yes. That is what I showed. Yeah.
So when there is when very rapid diffusion occurs, the reaction will become so slow that virtually we will not be able to see any concentration gradient.
Anita, first part is correct. Next part is wrong. You are telling diffusion is rapid, so you cannot visualize
the reaction will become very slow, sir.
Why the reaction is becoming slow? You never know the reaction is becoming slow.
I'm not sure, sir.
Yeah, good try, but it's almost there. Yeah, some other people can refine on it. Yeah, in meanwhile you can also refine why the reaction gets slow there. That is the question to you, Anita. Just think about it. Yeah. Next, any other answer? Yeah, someone put hold. I don't know why. Sudarsh, you are on hold. I think. Did I put you on hold? No, I didn't put you on hold. You yourself kept on hold. Okay. Yeah. Any other? Prashant, PM. You are there? Okay. I think you are just thinking about what I told. Now let me give the explanation. Let me give the explanation here. Let me put this bit higher so that you can see. This fellow I'll put a push. This fellow I'll push. Put here. Yeah. Now what is happening? I don't know what is happening here. The red color is not coming. So here, this is the solid surface, right? And this is the gas. This is the gas, right? This is the gas resistance. This is the CAG, this is the CAS, and this is the reaction happening, right? Now what I am telling you is there is some resistance in the gas field, right? This you call it as Kg. There is resistance at this particular thing, that is nothing but K prime. That is what we call, right? Now, if I assume Kg is much greater than K prime, what does that mean? Kg is the mass transfer coefficient is very high. When the mass transfer coefficient is very high, what will happen to the diffusion? What will happen to the diffusion? It will be very high, correct? A high mass transfer coefficient, definitely your diffusion will be high. The rate of diffusion will be very high. What does that mean? Each and every molecule, it is not having any resistance here. The moment it is here, it will go here immediately without any resistance at all. So since Kg is very higher, 1 by Kg, this is what is the resistance. 1 by Kg will be very less. That is, the resistance in this is very less. That is, there is no fighting among G at all in between that. That is just like you are in one room, and if there is no door at all, that is boundary at all, and if something happens in the room and which you need to go out immediately, some emergency, then what will happen? No resistance, right? Because the wall is not there. All people will come out immediately. If there is a wall, then there will be fighting among each other to come through a particular opening. In that process, your resistance will be high. When there is no resistance, that means that literally no time is spent in that. Did it make sense what I'm telling?
Yes, sir.
So when there is a very high resistance, when there is a high mass transfer coefficient, 1 by mass transfer coefficient will be the resistance. The resistance is slow in the sense the time for the molecule to go from this particular to this is very less. Immediately, the moment you are in the bulk, it is going to the solid surface. So Kg is very high in the sense the mass transfer coefficient is high, the resistance is small, there is no infighting. That is, this resistance is literally not there. So the resistance only it is present here on the solid surface. So that is why it is called as a chemically reacted control, because this is the slowest step. Here there is no, the moment it is here, it is going here very fast within milliseconds. But it is taking more time here because your overall reaction time is nothing but from here to here plus here to here, whatever reaction. This is very small. This is very more. Therefore, the overall reaction or overall time for the reaction depends on this particular step. Just like I told in the previous example also. This is from SSN College. This is from SSN College. And this is the Sholinganallur junction. Let it is going to the Thiruvanmayur here, somewhere, core or whatever you call, right? This Thiruvanmayur. So, if there is no resistance from college to Sholinganallur, immediately you can go to Sholinganallur, right? There is no resistance. The time required will be very less. And if at the Sholinganallur too much of traffic is there, you get more resistance here. Therefore, from Sholinganallur to go to the Thiruvanmayur, it depends on how much time you are spending at the Sholinganallur, because the resistance is more here. If, for suppose, here there is no resistance, near the Sholinganallur there is no resistance, your more traffic is in this particular, from college to Sholinganallur, then this controls your resistance, because that is where you are spending more amount of time. Your total time will be the sum of the times of this and this. If this is very less and this is very more, your total time will have only this quantity more than this quantity. Now, does it make sense now? Now, I'll go back to this particular slide. Minus Ra prime is this. So, this is like this. This is the solid, this is the gas, and this is the resistance. This is kg and this is k prime. Now you are assuming k prime, kg is much greater. Kg is much greater in the sense 1 by kg will be the resistance, individual resistance, that is very less. Therefore, the time required for the molecule to go to this surface is very less. Your total time for the conversion is this time plus the conversion time. That will be the total time. So total time is less time here plus here if there is some resistance, that time, resistance time. So this is very less, this is very more. So you can cancel out. The total time is nothing but this time. That is what is called as this is controlling step. Whenever there is a resistance more, that is the controlling, because the time required for it to react here, it will take more time. Understand? So if this is more, if this is less, that means that the diffusion is taking more time. Once it diffuses to this particular step, that is surface, immediately it is getting reacted. There is no diffusion resistance on the surface. The moment the solid is coming onto the surface, it is immediately getting reacted. But the reaction is taking more time here. The resistance is taking more time because it has to cross through the bulk phase. So it is taking more time here. Then you call it as mass transfer control. If there is a mass transfer control, that means that the diffusion is playing a very important role. Yeah, does it make sense now? Now you can see the diffusion is very rapid. Here it is very rapid, but the reaction is very slow. On the surface, there is too much of resistance to react. Maybe the solid is not that much porous, or whatever may be the reason. But if the reaction is very rapid here, that means that there is a resistance here. Therefore, in the bulk phase, if you can increase your kg, that is mass transfer coefficient high, then your reaction time becomes very less. Yeah, does it make sense what I told? Yeah. Not able to understand?
Yes, sir. Yes, sir. It does.
It's just like I gave one more example, gulab jamun. I'm placing a gulab jamun in the sugar syrup. This is the sugar syrup. This is the sugar syrup, and this is the gulab jamun. G, gulab jamun. Gulab, G-U, gulab jamun. J, GJ. So if there is a resistance in this sugar syrup, that is, we are assuming it is gas, this sugar syrup will go and stick there itself. It won't go inside because too much of resistance is there. That is, if the sugar syrup is very thick, then it won't penetrate through this porous. It will stay there. That means that there is a resistance here. Now let us assume one more. If this is too much porous, big holes are there. Big holes are there on the gulab jamun. Then what will happen? Immediately it will go inside. Right? So that is what you mean by resistance or whatever you call it. Just imagine like that. The moment the one sugar syrup is going inside, immediately it is going inside. There is no resistance inside. Only the resistance will be there on the surface itself. That is what it means, surface resistance. Any other doubt? I don't know. I made it sense or not. Does it make sense? Anita, I think you got some point, whatever. Now, does it make sense, Anita?
Yes, sir.
Yeah, fine. Yeah, any other you want? I think time is running out. Yeah. Shall I go to the next one? Does it make sense? No answers. Okay, think about that answers.
Yes.
Let us go to the next one. These are the ideal contracting patterns. Because the solid reaction when it's taking place, you have to know which phase because there are two phases, two reactants of different phases. that reactant, how they are going to get contacted. Because if you want to design a reactor, you should know what is the kinetic term. That is what we discussed in the CRE1, kinetics. Not only kinetics, how they are going to contact, whether they are going in a plug flow or they are going in a mixed flow, or one is coming in a mixed flow or one is coming in a plug flow. Based on that also your equation, design of an equation changes. So ideally, A and B, let it be the reactant. So both can go in a plug flow. This is the reactor. A is going like this, B is going like this. So both are, A is a plug flow, B is a plug flow, it is a counter current. So if you want to design this type of reactors, it is better always to go for a plug flow design expression. Correct? You know what is plug flow design expression, right? V by F A naught is equal to 0 to, what is that? Integral V by F A naught, sorry. V by F A naught is equal to integral 0 to XA dXA divided by minus RA, right? This is the desired expression for plug flow. It can go as a counter current also. It can go as a cross current also, like this. The other way. As long as there is going in a plug flow, you won't have any problem, because you know what is plug flow, right? Plug flow is like a pipe. So the reactant molecules is not coming back. There is no, there will be no radial mixing may be there, but actual mixing, the point here and the point here, it won't mix. It is going in a straight line. You won't have any problem if there is a plug flow. But sometimes A is going in a plug flow like this, but B can be a mixed flow like this. B is going in a mixed flow. Then when any reactant is going as a mixed flow, this is where it gets created a problem, because mixing creates uniformity. Mixing creates a uniformity. When there is a uniformity, your concentration immediately is getting dropped. Correct? Because as long as the reactant is going in a plug flow, your concentration is holding very high. Therefore, the rate will be very high. Whereas when there is a mixing, the concentration is dropping suddenly. When the concentration drop is there, your reactant conversion also will be less. So when it is going in a mixed flow, you have to understand whether that particular mixing is because of mixing, whether the fluid is going as a microfluid or a macrofluid. You know what is microfluid and a macrofluid. Microfluid in the sense, everywhere the concentration will be uniform. Macrofluid in the sense, just like in your class, you will have groupisms, right? Boys group, girls group, or CBSE group, or state board group, like that. Different groups will have different concentrations, or different groups will have different level of understandings. So this is where it gets a problem. When it is going in a microfluid, then it creates a lot of problem, right? Yeah, I think it came, I don't know why. So it can go as a microfluid or a macrofluid. Sometimes what can happen is, A also can be a mixed flow, B also can be a mixed flow. Either it can go as a microfluid or a macrofluid. This is the biggest disadvantage. So any of the reactant ideal contacting patterns for contacting two fluids in a reactor, it will fall into one of this particular thing. This is ideally. Non-ideally, n number of things will be there. Okay. Yeah, I'll stop this here. I don't want to continue more than this. Then we'll continue next class. Yeah. Today's class, how many of you it made some sense? So I did one important derivation here. Now, the moment I tell reaction is controlling, then immediately you have to get into picture that this is the equation. If I tell mass transfer is controlling, then you have to get this into picture. So reaction is controlling in the sense you should understand what is the step behind. The diffusion is very rapid, the reaction is very slow. If I tell mass transfer is controlling, that means that surface reaction is very rapid, but the main time it spends is in the diffusion part. So based on this, if you go to some interviews, all that, they'll ask a lot of questions. You have to be clear in mind. What does that mean? Okay. I stop the recording. Yeah, any doubt?